Good morning, everyone. This is lecture 9 of AREC 333. The topic of today's lecture is going to be mainly on the technical aspect of production, but from the multiple input perspective. So in the last few lectures, we finished the one variable input production part. And again, starting with the multiple input, we will first go over the technical aspect. Then after that, we will do profit maximization from both the input perspective and the output perspective. You will find out that there's a little bit more stuff for the multiple input production function. But a lot of the concepts and ideas are basically the same as those you have learned from the one variable input production function. For today's lecture, we will be mainly focused on the technical aspect of production. However, before that, I will do an overview of profit maximization for one variable input and do a comparison of the input perspective and output perspective. What's the linkages between those two perspectives, and why do you get the same results by solving profit maximization from the two perspectives? And then after that, for the multiple input production, we will first, similar to those one variable input, we will first introduce the average and the marginal productivity concepts, APP, MPP, and then after that, there's some new stuff called isoquant. And in lab 2, we actually introduced when you have the multiple variable function, then the what's the level curves, how do you get the level curves? Isoquants are actually the level curves if the function of interest is your production function. And then after that, I hope that we will have time for the returns to scale. That will be based on the level curves for or the isoquants for multiple input production function. And I also put in this outline the marginal rate of technical substitution. However, I don't think we have time for that today, but this is to give you a heads up. The suggested reading here, I recommend that you mainly read DeBertin 2012. Rasmussen, I think, already assume you have some knowledge of production economics, and so actually Rasmussen here, I don't recommend it. It's too there's not much details in that, and actually for the first time that you're learning production economics, it might not be that friendly to you. And if you do have the BD et al. Book, I would recommend that you read that section. If not, don't worry. And if you do listen or watch this lecture well, I'm pretty sure I covered most of the contents in that section that I think you should know. Let's first have the overview of the profit maximization from the two perspectives, and I will write them down here, and the input perspective on the left side, the output perspectives on the right side. And to do a profit maximization, you actually need to first have the profit function. So for the input perspective, it's a function of X, and for the output perspective, it's a function of Y. And so we have different terminologies to describe the components of profit for those two perspectives. The input perspective, it is the total value of product minus the total factor cost, which is also a function of X. So you will notice that in the input perspective, everything is written in terms of X. On the other side, for the output perspective, the profit is a difference of total revenue and total cost. So you will notice here on the left, everything in X, on the right, everything in Y. And we do have a, to solve the profit maximization, we actually mentioned there are 3 conditions. First is the first order condition, the second order condition, and also the total condition. Here I will mainly focus on the first order derivative. So from the input side, to solve for the profit maximized input use, you need to take derivative of your pi with respect to your choice variable here. So the choice variable is your input use. And we sometimes write this as pi prime. And if we take the derivative of pi, then it is just taking the difference of the derivatives of the 2 components of the profit function. And here everything is taking derivative with respect to x. So here, let's actually further simplify this, is because we defined the derivative of TVP with respect to x. We know that is MVP, and also the derivative of total factor cost with respect to x is MFC. So to solve for the input that will lead to maximized profit, we set the first order condition to equal to 0. And same thing with the output side. However, this time y is a function, pi is a function of y, and you also, when doing the derivative, you need to be very careful here. You're taking derivative with respect to y. So if we again, we can write this as a difference between the derivative of total revenue and the derivative of total cost. So here again, we set the first order condition, or the derivative of pi equal to 0, and derivative of total revenue with respect to y is your marginal revenue, and derivative of total cost with respect to y is your marginal cost. So I hope now if you look at those 2 conditions, you're clear that MVP and MFC are concepts for the input perspective, and MR and MC are the concepts for the output perspective. So here we have the 2 conditions, and I'm going to show you that they are actually linked. And if you solve one, you're also solving the other. Or if one of the condition is satisfied, then the other condition is also satisfied. And we will need something called the chain rule that I covered in the first lab session. So pi, if we write pi as a function of x, and then here pi is actually a function of your output first, and then your output is also a function of x. So this is when you're taking your derivative of your profit with respect to x. Then the chain rule said is that you should first take derivative of pi with respect to y, and then at times the derivative of y respect to x. So if you're doing this way, then this derivative of pi with respect to y, we have just write it here, is mr minus mc. And on the left side, if you're taking derivative of pi with respect to x, then that lead to MVP minus MFC. So on the left, it equals to mr minus mc times something here. So what is dy over dx? Taking derivative of y with respect to x. I hope right now once I say that, then MPP immediately is the answer. So we can see here the first order condition from the input perspective and the output perspective are actually linked by MPP here. And if you set MR minus MC equal to 0, as long as MPP doesn't equal to 0, then this condition is also satisfied. So if you do solve your profit maximization from the output perspective, then you also solve it from the input perspective. The result that you will get will be exactly the same. And so this is the link between those two perspectives. And we also covered the case of the perfect competition assumption in both factor and output markets. And if that's the case, then what we have here is that MVP is your P times your MPP, and MFC is your R. So those are the first order conditions from the input perspective, and from the output perspective, MR will equal to P, which is the output price, minus MC times MPP. So the condition can be simplified. And if you do expand this term and write it this way, you will find out that the P times MPP can be canceled, and you got this condition of R equals to MC times MPP. So again, that is because of the chain rule. However, I do hope that you realize here that the two perspectives are the same. You got, if you solve it from the two perspectives, the maximum profit in number, for example, how much dollars will be exactly the same. This is a summary of the link between the two perspectives, starting from TPP, and then I actually showed in lecture how you can go from TPP to variable cost. And here, BD et al. Just have a more detailed summary of all the linkages between all of the optimality condition and also those concepts from the two perspectives. So I do recommend that you spend some time trying to figure out how are the different graphs or subgraphs are linked together. I can assure that if you can figure that out, then you have a very good understanding of what has been covered in this course so far. So far, what we have covered are, we say that there's only one variable input in the production process, and all of the rest of the inputs we consider them as fixed. That is for illustration of the production functions or the concepts and the principles. However, in reality, there's very rare that a production only use one variable input. And the real case is that usually there's many variable inputs, and the producer have to decide on which what's the best combination of those inputs in order to either maximize profit or minimize cost. So starting from now, we will be focusing on production function with multiple variable inputs. And as I have explained in the last lab session, the two variable inputs case can actually be helpful for you to understand. A lot of the cases we are able to draw a 3D graph to represent the two variable input case. However, the multiple variable input case, for example, if you have 3 or more variable inputs, the idea behind that will be the same as the 2 variable inputs. So for this course, we will be focused on 2 variable input case. Here, on the top is the short run one output, one variable input production function. And if we have 2 variable inputs, then we put x1 and x2 on the left. That will be conditioning on x3 until xn. Those we assume they are fixed. And again, for notational convenience, we just write y as a function of fx1 and x2. Here are a few examples of the 2 variable input production function. The first one is a linear production function. The second one is a quadratic production function. And then the third one, we call it generalized Cobb-Douglas production function. Right now, you only need to know the name that there's a Cobb-Douglas function. Later on, we will spend some time to discuss Cobb-Douglas function in general. Once we are done with both the technical and the economic aspect of production for multiple inputs. So if you have a two variable input production function, here is what the production surface might look like. So for 1 variable input, we have a curve, and for 2 variable input, then we will have the production surface. I did spend some time introducing this production surface in lab session 2. So if you want to know more details, please watch that video. And here on the vertical axis, we have the output level, and on the 2 x1, x2 axis, those are the 2 variable inputs. If we're holding, for example, x2 constant, maybe at x2 equal to 0, then you can actually say from this graph that we can say that once we hold x2 constant, then we got a production curve that looks very similar to the production curve we have met before. So if we put the axis here, on the vertical axis, we have y. On the horizontal axis, we have x1. And this is actually the production function when you're holding x2 constant. So instead of having a surface, now you do have a curve. So again, if you look at this curve have the 3 stages. And to the right, here you'll have the stage 3. Some production surface might not have stage 3. Here is just to show you what it might look like if you have a production surface. Similar to the 1 variable input case, let's start with the APP concept. So in the 1 variable input case, we only have 1 APP. However, now if we have 2 variable inputs, then we will end up with 2 APPs. APP1 here is defined as the average productivity of input 1. So it's y divided by x1, the output per unit use of x1. So what is different here from the 1 input case is that this is average productivity of x1, of input 1, if we're holding x2 constant. And similar for APP2, that is the per unit output or per unit use of x2 of the output if we're holding x1 constant. Let's again use an example to illustrate the idea of APP. So here we are having a crop yield production function, which has 1 output is y, and there's 2 inputs here, 2 variable inputs here. 1 variable input is nitrogen, and the other input is, you can think of that as potash. So again, this is a quadratic production function, and we can actually calculate the average productivity of nitrogen and average productivity of potash. So N here will be the X1 and P will be X2 in the previous slide. And the calculation here are pretty straightforward. I will not go over them, but you should verify that I did everything here right. And if I did something wrong throughout this course, let me know. I will need to correct them. The MPP concepts, again, will also be similar to the one variable input case. And the only difference here is that instead of using D, so remember in the Y input case, we have MPP equal to dy over dx. So D is the derivative when you're having one variable input, and if you're having two variable inputs, and here we have to use this letter, this Greek letter here. We also say it's dy, but it's partial. So this is partial y with respect to partial x1. And this is the rate of change of the output with respect to x1 if we're holding x2 constant. So if we are increasing x1, the use of x2 by a little bit, then MPP1 is measuring what is the increase in y due to that small increase in x1. And the same time, we're holding x2 constant. And if you have a difficult time understand this, you should watch, again, lab session 2. There I introduced the partial derivative concept. So MPP2 will be very similar. However, here we're taking partial derivative with respect to x2. So these two MPP concepts, sometimes MPP1 might be a function of both x1 and x2. Sometimes it's not, depending on the type of production we have. So you need to keep that in mind. With the MPP concept well understood, then we actually are able to calculate the maximum technical output if we're giving a production function. So this is again the same production function, same example, and similar to the one variable input case. If we want to find out the maximum y, then we're taking derivative of y with respect to x and set that equal to 0. So that's the one variable case. And for if you have two variable inputs, then I should mention this is a first order condition. We can ignore the second order condition and the total condition for now. So the first order condition when you're having two variable inputs should be depending on how many variable inputs you have. So if you have two variable inputs, then there's two first order conditions. If you have n variable inputs, then there will be n first order conditions. So here, the two conditions will be the partial of y. Oh, sorry, this should be y here. So partial derivative of y with respect to x1. x1 is n here, that equal to 0. And then another condition is partial derivative of y with respect to p equal to 0. And the partial derivatives are, again, what we have just defined. It's the marginal physical product. So if we want to find out maximum technical output, we set the partial derivatives all equal to 0. And again, the reason that we say this is technical, this is compared with the economical. So the economic concepts. Technical means everything is in physical terms. For example, the yield will be kilograms or something similar. However, if it's economic concepts, then it might be dollar values. We will assign price to the output or the input. So if we want to decide that, we first find out the MPP for the two inputs. We set them equal to 0, and then we have two unknowns and two equations. And using substitution, we will be able to solve the optimal N and optimal P. So once we say that's optimal, we put a star here to indicate that's the optimal input use. And if you do got those two optimal input level, then plug them back into your production function, you will be able to get the maximum technical output. Again, I will ask the question again, is that will this maximum output lead to profit maximization? And the answer will again be no. And once we get to the economic aspect, we will explain how you find the optimal input use that will lead to maximum profit. And it's different from these two levels that is leading to the maximum output. When we are having two variable input, sometimes there's synergies between the use of that those inputs. Sometimes those inputs might be independent. So we actually use a term here which is called technical independence to explain that dependence. So what we're interested is what happens to MPP for one input. For example, in the previous example, the MPP for nitrogen, if we change the use of another input. So for example, if we change the use of potash, then what is the MPP for nitrogen? So that is actually another partial derivative. It's partial derivative of MPPI with respect to xj. So the I and j here are different. So to make it more concrete, it can be MPP nitrogen with respect to P. So if that derivative is positive, then we say they are complementary inputs. So that means is that the use of P will enhance or reinforce the marginal productivity of nitrogen. So if the derivative is negative, then the inputs are competitive. And if that derivative is 0, then they are the inputs are independent. That means that the use of P have no impact on the marginal productivity of potash. Let's actually do the calculation here. So from the production function, we already are able to write the MPP for nitrogen. And if we want to know the technical interdependence between N and P, then we can take derivative of MPPN with respect to P. So taking derivative of this equation with respect to P, and derivative of constant equal to 0. If we're taking derivative with respect to P, N is considered as constant here. So the derivative is also again 0. And we find out this is the only thing left. So this number is greater than 0, which means that N and P are complementary. So again here, we should pay attention that what we actually started is MPPN and taking derivative with respect to P. However, if we start with MPPP and take derivative with respect to N, we will end up with the same result. So you might want to do that, actually write down the MPPP and take derivative with N and verify, you will find out the same same number here. So that's just the property of derivatives. Another similar concept is factor elasticities, or sometimes we call it elasticity of production. So even if we call it elasticity of production, you should keep in mind that it is elasticity of factors or inputs, because we're gonna learn some new elasticities. So do keep that in mind. So in the two variable input case, we have two factor elasticities. And to give you an overview of the elasticity, factor elasticity is the percentage change in output, or in Y, due to the percentage change in input. So here E1 is the change in Y, percentage change in Y, that's dy over Y. And then on the denominator, we have dx1 over x1, so that's the percentage change. If we rearrange the terms again, similar to the one variable input case, the elasticity can be written as the ratio of MPP and APP. So E1 is MPP1 over APP1, and E2 is MPP2 over APP2. Later on, we will introduce another elasticity concept called elasticity of scale, and it's linked to these two elasticities here. Remember, from the one variable input case, we can use the value of elasticity to decide the stage of production. It's the same for the two variable input case, but in the two variable input case, we're deciding the stage for each input. So remember that, so this is a one variable input case. If elasticity is greater than 1, then we're in stage 1, and elasticity is between 0 and 1, we're in stage 2, and elasticity is smaller than 0, then we are in stage 3. So again, let's use the crop yield example. And we already learned how to calculate the MPP and APP for those two inputs, P and N. And to calculate your elasticity, you actually just took the ratio of MPP and APP and use the MPP and APP equations we have derived. And if I give you specific P and N values, then you can write this En, which is the elasticity here, and you calculate the value for MPPN and the value for APPN. Then you will be able to calculate the elasticity. So here we have the elasticity for both N and P, and we notice here that two elasticities are both between 0 and 1, which means that both inputs are in stage 2. And if we are having a different value of N and P, so now we're having different input use, then again, we can calculate the elasticity again. And you will notice here that for N, the elasticity is between 0 and 1. That is in stage 2. However, for P, which is which we are having a negative elasticity, so elasticity is smaller than 0, that means that P is in stage 3. It's interesting to notice here that different inputs could be in different stages. And for production function with two variable inputs, in order to produce the same level of Y, you actually have many different combinations of input use. And again, it's possible. We mentioned that in the one variable input case, it's never optimal to produce in stage 3. However, here in the two variable input case, it's possible that one variable is in stage 3 and the other variable is in stage 2. This graph is the isoquant of the production surface that I have shown you at the beginning of the lecture. So the isoquant of this production surface. So isoquant is for each level of y, if you keep track of all the same level of y on this production surface, and then if you project that same level of y to the x1, x2 space, then you will get this graph here. So each curve here means it's the same level of y. For example, this curve, this y dashed curve means it's y equals 213. And this isoquant is actually get if you slice your production surface with a plane that is horizontal to the x1, x2 space. I did spend some time in the lab session explain how you get this isoquant, or in the lab session we call it level curves. However, if your production surface is if your production function is a function of interest, then the level curves are called isoquants. So iso means equal in Greek, and quant is just short for quantities. So again, that means in the isoquant curve, each curve means equal quantities. And again, here is another isoquant curve, and each curve means the y level or the output level is the same. So if you, I'm sure you heard of the name indifference curve in your elementary economics course. So isoquant here is similar to indifference curve. And the difference is that indifference curve is from the consumer's side, and production for the production side or the producer side, then it's isoquant. And how if I give you a production function, then how can you actually draw this graph of the isoquants? Let's use an example to illustrate the idea. So assume this is your production function. There's two variable inputs here. And usually when we draw isoquants, we have x2 on the vertical axis and x1 on the horizontal axis. So if we want to put x2 on the horizontal axis, then we should, from this production function, solve x2 as a function of y and x1. So how do we solve that? We can actually, from here, we can write x2 to the 1/2 is equal to y divided by x1 to the 1/2, or we can write it another way, is y times x1 to the minus 1/2. And then we can go one step further, is x2 will equal to y times x1 to the minus 1/2, and then square. And if we simplify this expression, we will get y squared over x1. So this is the equation for the isoquant. And to get all of those curves in the graph, you need to actually, once you get this isoquant function, for example, you fix y equal to 1, then your x2 is equal to 1 over x1. And let's say this is a y equal to 1 isoquant, and then you set y0 equal to a different value, And then you can write x2 equals to 4 over x1, and that might be this curve, y equal 2. So the isoquants are the same level of y. However, you can see here, to get the same level of y, you can have different combinations of x1 and x2, and you achieve the same output. And why are we using the isoquants? It's because sometimes the 3D graphs are difficult to visualize, and if we can draw the isoquants curve, then we actually convert the 3D graph into a 2D graph. And with the isoquant curves, we can actually show the concept of returns to scale. Later on, we can also show the marginal rate of technical substitution. Let me actually show you the returns to scale first. We actually have already saw this term returns to scale when we studied the one variable input, but I didn't mention this concept at that time. So we already learned the diminishing marginal return when we study MPP. And let me actually first define what is economies of scale, and then I will show you how you can tell from a graph for both one variable inputs and two variable inputs. How can you tell whether you're having a increasing, decreasing, or constant return to scale? So economies of scale, it is describing how much production increase, or the production here is Y. So how much Y increase when the firm or the producer increase its scale of production. And what is a scale of production? It means that if the producer increase all inputs by a proportion. So for example, if there's only two inputs that the firm use, N and P, that means if the firm increase P twice and also N twice, then what is the change in the output in Y? So again, it's basically what happens to the amount of output if all inputs are increased proportionally. There are three returns to scale: constant returns to scale, decreasing returns to scale, and increasing return to scale, CIS, DRS, and IRS. So when we see we have constant return to scale, that means if we increase all inputs by 5%, and the output also increase by 5%. So the output increases in the same proportion as input. Then we're saying that this is a CRS production technology. Decreasing returns to scale means that if all inputs increase by 5%, then the increase in output is 4%. That's less than the 5% increase in inputs. And for increasing returns to scale, it's saying that if all inputs are increased by 5%, then your output is going to be increased by 6%. That's more than 5%. And in the typical production function for one variable input, we actually there's actually both increasing, decreasing, and constant return to scale there. Let's actually figure out why. The return to scale for one variable input case is fairly easy, and we can tell from the shape of the production function and also the shape of the MPP curve. We can tell whether it's constant increasing or decreasing return to scale. In the one variable input case, we don't need to worry about the proportional increase in all of the inputs because there's only one input. So let me actually start with the simplest case is when we are having a linear production function. And if that's the case, let me draw this linear production function here. Then for each additional input use, we get the same level of increasing output. So here, for example, if the input is increased from 1 to 2, then the output is also increased from 1 to 2. So if we further increase the output for from 2 to 3, the increase in output is also the same. So if we draw this if we draw the MPP curve of this production function, then the MPP is actually constant. So if the MPP is constant, then we're having a constant return to scale. So for one input case, it's really easy. And let's look at a second case is where if the production function is something like this, then we are having a increase in return to scale. It's because for this production function, if we draw the MPP curve, then the MPP should be upward sloping. It could be a straight line or this curve or this curve. It doesn't matter. If it's upward sloping, then we're having increasing return to scale. Here we're having constant return to scale. And the last case is where our production function is having this shape, then the MPP curve will be downward sloping. So it's decreasing as more input is used. It could be smaller than 0 if we're having an MPP curve like that. So this is a decreasing return to scale. And the typical production function that we have been studying actually have both increasing and decreasing returns to scale. If you argue there also could be a small portion of it where there's constant return to scale. Let me explain this to you. So first, let me draw this production function, and let's say this is the inflection point. So the inflection point is where the MPP reaches its maximum. So let me draw this. This is the MPP curve for this production function. And at this point, the MPP should reach maximum. Excuse me about my drawing. And so to the left of the inflection point, the output is increasing at the increasing rate, and the rate is MPP. The MPP here is increasing. So that's the portion of the production function we're having increasing return to scale. And then along the production curve at this range, and it kind of looks like linear, and we can argue that at that part, it's having a constant return to scale. Then to the right of the inflection point, then the MPP curve is actually decreasing. So for that portion of the production function, we're having decreasing return to scale. So that's the one variable input case. For production with 2 or more variable inputs, then it is very difficult to tell from the production surface whether it's having constant increasing or decreasing returns to scale. We can probably still tell for 2 variable inputs because we can still draw the production surface. However, if there's even more variable inputs, then it will be difficult to tell from the graph. And the use of the isoquant curve actually can help. Let me stop here today, and next lecture we will continue with returns to scale for two variable inputs, and then we will also discuss the rate of technical substitution between two inputs. And if we have more time, we will go with economic aspect of multivariable production.